In this primer, we discuss the architectures of FIOS, UVerse, and DOCSIS, comparing the advantages and disadvantages of each. If you haven't already done so, you might want to first have a look at our previous tutorial called Network Evolution, which describes what happened in the outside plant prior to the evolution of FIOS. To review quickly, the migration of electronics from the central office to the outside plant was driven by the Babybel's need to reduce wire congestion, serve longer distances, and relieve wire pair shortages. Back in the 1970s, prior to the days of the Internet, there was little need to provide additional bandwidth to phone subscribers. However, the Bells quickly realized that the movement of electronics closer to the customer also meant that they could provide more bandwidth to the home. Let's see why this is so. Consider the architecture shown, where a fiber terminal terminates a fiber originating from a central office and then feeds a copper loop to a subscriber's home. Fiber optic link shown in this diagram is never a bottleneck for bandwidth. The physics of the copper loop, however, does not allow this medium to carry as much bandwidth as the fiber optic line. As the fiber terminal moves closer or farther away from the customer home, the length of the copper loop is lengthened and shortened accordingly. As the loop gets larger, the resistance in the copper wires becomes larger, and therefore making current drive more difficult, thus slowing the available transmission speed. Conversely, as the fiber terminal gets closer to the customer's home, the loop length gets shorter and greater bandwidth is possible. Thus we conclude that the shorter the fiber optic terminal is to the customer's house, the greater the bandwidth the customer can receive. The two surviving Babybels have decided to deploy different architectures for serving fiber to their customers. AT&T has chosen its UVerse architecture, which deploys the fiber terminal curbside and serves a maximum of 50 homes from each such node. In comparison, Verizon's FIOS system has taken an ONU, a fiber optic terminal, and terminated it all the way on the side of the customer's home, thus providing a fiber for each of their customers. In comparison to this, cable uses its old hybrid fiber coax architecture, which terminates a fiber somewhere in the neighborhood and serves a cluster of homes, often in the hundreds. Historically, cable TV systems have been better adept to providing downstream bandwidth than upstream bandwidth. We describe the upstream portion of the bandwidth as getting larger, and therefore the systems getting closer to symmetry as cable systems migrate their systems to the new standard called DOCSIS 3.0. Although both cable systems and Verizon's FIOS system has better ability to serve downstream bandwidth than upstream, Verizon's FIOS architecture is much closer to providing symmetrical bandwidth levels and is often referred to as a star architecture compared to the cable system, which is described more as a branch and tree. In comparing Verizon's FIOS to AT&T's UVerse, we note that FIOS costs more, particularly because the terminal that terminates the fiber is one per subscriber, whereas in the AT&T UVerse system, the fiber terminal is shared among multiple homes, often as many as 50. However, in return for this additional cost, the reduction in length of the copper loop allows the FIOS system to deliver more bandwidth, especially upstream, per customer. Although not discussed further in this tutorial, AT&T's UVerse system uses IPTV for TV transmission versus Verizon's video service, which is passband. So how much does FIOS cost? The proponents of FIOS claim costs of around $3,200 per subscriber and heading lower each year. They claim costs of $800 per home passed, mixed with 25% penetration, meaning 1 in 4 homes taking the service, yielding a cost per subscriber of around $3,200. Opponents claim, however, that the actual costs are closer to $1,000 per home passed and that penetration is likely to only be around 10%, thus resulting in a cost per subscriber of a whopping $10,000. In comparison to this, AT&T's UVerse system costs only a fraction, well under $1,000 per subscriber, because a key portion of the network, including the terminal that terminates curbside, is shared among multiple homes. In comparing FIOS against cable's DOCSIS 3.0 standard, we note that FIOS will cost significantly more to implement because it represents a forklift upgrade of Verizon's existing plant compared to the evolutionary DOCSIS 3.0. FIOS delivers more bandwidth, however, especially in the upstream link. FIOS is more like a star architecture, where DOCSIS represents a continuation of the cable company's existing branch and tree architecture. A key part of the new DOCSIS 3.0 standard calls for the cable companies to recoup the portion of the bandwidth from 42 MHz to 85 MHz that is currently used to house lower TV channels to be reclaimed for transmission for upstream bandwidth. However, the existence of legacy equipment inside the cable company's fiber node, specifically the presence of amplifiers and diplex filters, may make it difficult for these companies to reclaim this bandwidth, as many of these diplex filters are tuned to the existing frequency map and cannot easily be changed out without causing service interruptions. Thus, we expect that in the near term, FIOS might maintain a significant bandwidth advantage over DOCSIS 3.0 implementations, especially in the upstream direction. In comparing UVerse to the DOCSIS 3.0 cable standard, we note that UVerse still costs more, but not nearly as much as FIOS. DOCSIS does deliver more bandwidth, but only if it can overcome the legacy issues we recently discussed. VDSL remains the choke point for UVerse architectures. While the fiber link between the central office and the curbside terminal is never a bandwidth, the VDSL copper loops that run from the curbside terminal to the home represents the single most important choke point in a UVerse architecture. Specifically, the upstream bandwidth is likely to be significantly less than FIOS and even less than what DOCSIS 3.0 provides. In a cable DOCSIS 3.0 upgrade, multiple channels are typically bonded together to increase the available bandwidth. For example, the bonding of 4 such channels allows 160 megabits per second to be delivered in the downstream direction. However, this amount of bandwidth is typically shared across all the homes that serve a particular fiber node. Depending on the number of homes and the amount of bandwidth each uses, will determine the average bandwidth available per home. In comparison, FIOS' latest GPON standard allows for 2.4 gigabits of downstream bandwidth and 1.2 gigabits of upstream bandwidth for a cluster of up to 32 homes. We expect Verizon's system to continue to deliver higher amounts of bandwidth versus DOCSIS 3.0, but to scale at a much slower rate. An apples-to-apples comparison of speeds remains difficult because it varies on many factors, depending on how many homes are served per fiber node and the peak demand and the usage rates applied for each subscriber. However, for both industries, it remains a goal to be able to reach 20/20. That's 20 megabits of upstream and 20 megabits of downstream at a nominal cost of about $50 a month. We believe that the upstream delivery of 20 megabits per second will remain a challenge to both UVerse and DOCSIS 3.0 architectures for the reasons we have described in this tutorial. In summary, the battle between the cable and fiber to the X architectures pits cost versus upstream bandwidth. Because Verizon's FIOS forklift upgrade has few legacy problems, it is likely to deliver more bandwidth in the near term, but at a far greater cost. The cable companies will fight back with DOCSIS 3.0 channel bonding and dynamic frequency assignment, but the presence of legacy gear in their networks will make upstream bandwidth improvements more challenging.